Welcome to Topology Lesson 8 on metric spaces. We're going to talk about open sets. We'll define them, give a few examples, and then prove a few very basic theorems about open sets. The following lesson will be on closed sets, which are closely related to open sets. So just as a very simple example, in two-dimensional Euclidean space, this gray disk without its boundary is an open set. You can think of a disk centered at the origin with radius 1, including all points within the distance 1 from the center, but with not including the points on the boundary. And the defining characteristic is you can pick any point in this disk and then find another disk, an open ball, that encloses the point and is completely contained in the open set. So we can get as close as we want to the boundary, and we could still find a very small disk about that point that's completely contained in the disk, the open set. So the open set, all of its points are interior points, basically. That's the definition, but we'll get to that in a minute on the next slide and following slides. So let's take an even simpler example from the one on the previous slide. You may remember from even grade school mathematics, we talk about the real number line, and we had open sets there. You probably remember things like 0, 1 is an open set because you don't include the two endpoints, and then another example would be from -3 to +4. So these would be open sets. And then if you include the endpoints, you would have a closed set. So -1 to 7 is a closed set, 5 to 13, and all the points in between form a closed set. And then you may remember also where you have things like not including the -1, but including the 7. So that would be neither open nor closed. In the real plane, R2, the interior of a circle is an example of an open set. And a disk circle on its interior is an example of a closed set. So we looked at this first one on the previous slide. So we can generalize the concept of open and closed sets for metric spaces, and that's what we want to do here. So we start with something called an open ball, and it's not what you think of as a ball. It could be something quite general, and I'll show you one example that doesn't really look like a ball, but we use the term open ball, and you take a point X and a radius R, and then the open ball is all points in your metric space that are less than a distance R from your given point X. So X is the center of the open ball and R is the radius. So we have an example here in three-dimensional space, three-dimensional Euclidean space, I should say. So you take a center here, the origin basically, the point 0, 0, and then radius 5. So that's a sphere centered at the origin with radius 5. Now here's the example I mentioned that looks quite different from a ball. In the metric space of continuous functions, which we mentioned in the last lecture, say on interval -2 to +2, the open ball was center, and it's actually a function here, f of x equals x cubed minus 2x, and with radius 3 is shown in the figure on the next slide. It'll be clear when you see that. In words, the open ball includes only functions, continuous functions, on the interval -2 to +2, which are within less than 3 units from our center, f of x equals x cubed minus 2x, for each of the value x in our interval here, -2 to +2. So let's see what that looks like on the next slide. Continuing with the example from the previous slide, we have our open ball here, and it's actually the darker gray area. The center is this function x cubed minus 2x. So it's this graph here that I'm highlighting, and it's between the minus 2 and plus 2. And so any function that doesn't get further away from this center by more than 3 units at any point in the interval minus 2 to plus 2 is within the open ball. So let's maybe just draw one in here. I'll draw it in red. So we could have a function like this, continuous function. So it never gets more than 3 units away from our center. This red function never gets outside of this boundary here of the ball. So any continuous function that fits in this gray area is within the open ball about our center f of x. We have a few definitions on this slide. Let's start with the union of all open balls about a given point x. Eventually, as you make the radius larger and larger, you're going to include every possible point in the metric space. So the union actually equals the entire metric space. And I just made a point here that the distance between any 2 points in the metric space is a real and finite number. That's the key point here. So eventually, when you take every possible radius and then the union of all these open balls, you're going to get the entire metric space. On the other hand, since the distance between 2 points is 0 if and only if the 2 points are the same, we have that the intersection over all possible radii of all open balls about a point x is only the point itself. So eventually you exclude all the other points, no matter how close they are. Eventually you exclude them when you make the radius smaller and smaller. And then when you take the intersection, of course, you only get the 1 point. We have a definition here. Let y be a subset of x. We write that as y subset of x. You've probably seen that notation before. The little underscore means it could possibly equal all of x. If you remove the underscore, then it's what's called a proper subset. And that means it doesn't equal all of x. But in this example here, or this definition, we leave open the possibility y could be all of x. So a point, little x of x, is defined to be an interior point of y if there exists a radius r greater than 0 such that the open ball about x of radius r is completely contained in y. So I showed you that on the first slide with our little example, and I had the red point and the open ball within the set. The set of interior points of y is referred to as the interior of y. So if you take all the interior points of a set, we call that the interiors, and we write that as int y, interior of y. Clearly, every interior point of y is an element of y, just by definition. So the interior of y is a subset of y. It could be all of y, but it's a subset of y. Yeah, and I mentioned this before about a proper subset, so I won't repeat myself here. Now, the punchline is a subset y of x is defined to be open in x, where x is our metric space, I should have said, if every point of y is an interior point of y. So in other words, if the interior of y equals y, then we define y to be an open set. In all cases, in other words, for all metric spaces, the empty set and the entire metric space are open sets of x, our metric space. let's look at some proofs, or actually some theorems and proofs. So the first one is an open ball of a metric space X is an open subset of X. So let's take any open ball centered at X with radius R. So just as a visual aid, I drew it here. This is our center X and radius R. We need to show that every point Y in this open ball is the interior point of the open ball. Then that would prove that the open ball is open, an open set, I should say. So since Y is an element of our open ball, then the distance between X and Y is less than the radius. So in other words, R minus this distance is greater than 0. Then take any Z, an element of our smaller ball here, and that would imply that just by the definition of this smaller ball that the distance from Y to Z is less than S. Then we use the triangle inequality, so the distance from X to Z is less than or equal to the distance from X to Y plus the distance from Y to Z. We just carry over the distance from X to Y, but the distance from Y to Z is less than S. So we can put an S here. And then this sum is less than R. Just that's from this inequality here. So that would mean that Z is an element of the open ball X centered at X with radius R, because the distance between X and Z is less than R. So Z would have to be inside of this larger ball, which is kind of obvious from the figure, but again, this is just a visual aid to help with the proof. It's not a proof in itself. We've proven it here abstractly. So every point in this ball here, we took a general point Z. So any point in this open ball is also in the larger open ball B of X R. So Y is an interior point of BXR, the open ball centered at X radius R. And that implies, since we took any point Y in here and we showed that it's an interior point, that means that every point is interior to the open ball. And that means this open ball is an open set. Okay, so this is typical of the proofs. I'm not going to draw the figure in every case, or actually in most cases I won't, but if you have trouble following the logic, you might want to try drawing a simple figure like this. Sometimes that'll help. But again, it's just a visual aid. It's not the proof itself. Okay, we have another theorem which may seem self-evident just like the first one, but we require a proof here. So the interior of a subset Y of a metric space, in other words, int Y, is also an open set. So in other words, the interior of int Y must equal the interior of Y. Again, that seems like it should be true, and it is. So let's do the proof. So to show the interior of Y is open, we need to make use of the definition, which means we need to show that every point Y in the interior of Y is an interior point of the interior of Y. That will give us this here. Excuse me. So since Y is in the interior of capital Y, there exists a radius R greater than 0, such that the open ball centered at Y, radius R, is inside of Y. So we have this here. If we can show that this ball is also in the interior of Y, then then we're done. Since the open ball Y with radius R, centered at Y radius R, is an open set by our theorem 62, for each x in this open ball centered at Y radius R, there's an open ball about x with radius S, which is contained in our open ball B centered at Y radius R. However, this open ball is in Y, and so we have the open ball about x of radius S is inside of the open ball Y, centered at Y radius R, and that's in Y. So that's just from this and this, putting that together, we get this here. So each x that we've taken from the open ball centered at Y with radius R is in the interior of Y because of this containment here, which implies this open ball is in the interior of Y, since each element of it is in the interior of Y, and that's what we set out to prove here. Let's look at another theorem. Any union of open subsets in a metric space is an open set. So the key word here is any. It can be an infinite set, and it could even be an uncountably infinite set. So the set that's larger than the number of the cardinality of the integers. So that's why we use this subscripting here with A, an element of A. This could be the integers, but it could be the real numbers. So you could have an uncountable number of open sets, and the union is still an open set in the metric space. That's what we want to prove here. So we take our union, or we take our set of open sets, and then we take the union of it here. We let Y equal the union, and we want to show that Y is an open set. So take any element Y, small y and capital Y. It must be that Y is an element of one of the sets in this union. So we'll say let's say it's Y sub B. Since Y sub B is by assumption an open set, there exists an open ball centered about Y radius R such that it's contained in Y sub B, but then we know that Y sub B is in this union, so it has to be an element, or it has to be a subset of Y, which implies Y is an interior point, small y is an interior point of Y, and thus Y is open. So fairly straightforward proof, and we didn't need to assume the cardinality of the indexing here. Could be anything. The above theorem works, and I mentioned this, works for an infinite collection of open sets, but the same is not true for infinite intersections. We'll have a theorem just following this, but let's do an example first. So consider the collection of open sets from 0 to 1 plus 1 over n. Let's just think about what this looks like. So when you put in 1, you get the open set from 0 to 2. And then you put in 2 and you get the open set from 0 to 1.5. And you put in 3 and you get the open set from 1 1/3. And as you get larger and larger, the open sets get tighter and tighter around 1, 0, and just slightly larger than 1. So if we put in 10, it would be the open set from 0 to 1 1/10. So the intersection of all of those would be the set from 0, and then they would all include 1. Because you never exclude 1 in any of the intersections. You're always even slightly bigger here on this side of the interval. So for example, if you take n equals 10 million, you would still get 1 over 1 plus 1 over 10 million, slightly bigger than 1. So you never exclude 1. So you have this set here. This is neither open nor closed. So that kind of dashes the hope that maybe the infinite intersection of open sets is also open. However, we have the intersection of a finite number of open sets is open. That's our theorem here. So that's of some use to us. Let's see if we can prove that. So we let y sub capital Y sub I, the set of these from 1 to n. So we have n sets be a collection of open sets in a metric space, and then we take the intersection of those n open sets. Take any y, an element of small y, an element of capital Y, this intersection. Since for each y sub I there exists radii r sub I such that the open ball about y with radius r sub I is in y sub I, capital Y sub I. So we have this here. Then you can kind of see where we're going here. Since we have just a finite number of these r sub i's, let r equal the minimum of all the r sub i's. Then r is greater than 0 since it's the minimum of a finite set of positive numbers. And so the open ball y of radius r is in all of the y, capital Y sub I, since we've taken the smallest out of all of these, so it has to be in each y sub I. But that implies that the open ball about y, centered at y, with radius r, is in y, since y is the intersection of all these, and thus y is an open set in here in this metric space X. So the key point here is it's finite. If this was a infinite set, then this sequence here of r's could potentially go to approach 0, in which case you won't be able to pick an r greater than 0 in order to make this stipulation, to make this stipulation here. A subset of a metric space is open if and only if it is the union of open balls. Let's prove that first. Let's prove first that the union of open balls is open. It's pretty straightforward because we already know from our two previous theorems that an open ball is an open set, and we also know that any union of open sets is open. So the union of open balls is an open set. Going in the other direction, let's take an open set Y, and then take any y in our any small y in our open set Y. Then we know by definition there's an open ball about y that's contained in our open set Y. And if we just take the union of all these open balls, we get Y. And we can reason to that as every element of Y is in one of these open balls, is just the way we defined it here. And then each open ball is a subset of Y, and so the union of these has to be a subset of Y. So we've showed Y is a subset of this, and the union is a subset of Y, and that means they're equal. That's basic set theory technique. I didn't write all the details, but that's how that works. Now, if you have a subspace and you have an open set in it, it's not necessarily open in the containing space. So I give an example of that here. We have the unit disk centered at the origin, and that's open in two-dimensional space, but the containing space, R3, this set is not open there. If you just think about it, in order for this set to be open in R3, you would need to be able to find a three-dimensional ball in R3 that encircles a point, one of the interior points of this disk, and is completely contained in the in our set here in our disk, which is not possible since you're going in another dimension now with the open balls in R3 are three-dimensional, and so they can't be contained in this set here. So in fact, the only open set in R2 that's also open in R3 is the empty set. We have this theorem which is kind of as far as we can get in terms of relating open sets and subspaces to open sets in the containing space. I'll read it here. It's a two-directional if and only if. The set A is open in a subspace Y of a metric space X if and only if there exists an open set B in X such that A equals the intersection of B with Y. So I'm not going to prove this here. I'll give you a reference. If you go to my book, there's a reference from someone called the Math Sorcerer. He gives a nice proof. He's pretty thorough. He also does a lot of book reviews, so you may want to familiarize yourself with that person if you're interested in math books. I'll give you an example. We'll identify the different A, Y, X, B with our example here. So let A be the open disk centered at the origin. So this is just the formal definition of A. And our set Y, our subspace, is R2. So we have A and Y. And then we want to find the B such that when we intersect that with Y, we get A. So B has to be in our set X. So in our case here, we let B be the open sphere centered at the origin. And you can picture hopefully the open sphere at the origin, and then cutting through it in the XY plane, there's this disk. And so if you take the intersection of the this sphere with R2, then what's left is just the disk, in which implies A is open. So not very interesting. We kind of knew A was open already, but this theorem holds in general. I don't think I used it later on to prove anything, but I'll put it here just for completeness. Then there's one more thing. I should have probably put this on a separate slide because it's really not related to either one of these theorems, but I guess I was just saving space here, and I put it at the bottom of the slide. So the two metrics, so two distance functions on a set X are said to be equivalent if they determine the same open sets. So you may want to think about that a little bit. You can have two valid metrics, say on R2, and they could very well give rise to open sets. If you recall from the first lecture, we talked about the taxi cab metric and the Euclidean metric on R2. So you may want to think about whether those two generate the same open sets or not. So I'll leave that as an exercise for the listener. So in the next lecture, the next lesson, we're going to talk about closed sets. I'll kind of give you a clue. It's just the complement. What's not, if you take an open set in a metric space and you take the complement, what's not in that open set, that's a closed set. And that's one way of defining closed sets. But it's kind of what you're probably familiar with from geometry in high school or even grade school when you talked about just open intervals and closed intervals. So for example, this unit disk here, if I made this less than or equal to 1 and I included the boundary, that would be a closed set. But again, we'll talk about that more in the next lesson.